Hey everybody, I thought it would be kind of fun to make kind of a video solution to some of these problems. Maybe helpful than more helpful than just showing the key. So I am going to try to do that. I'm not going to spend a ton of time, but I'll try to give a little bit of discussion on each of the problems. All right. So we're going in to first these Chapter 8 and Chapter 9 problems. Alright, so this is the first set of problems. A good thing to do is really, consider what this thing is. It's a nucleophile. How many carbons are in the nucleophile? Well, you got 1, 2, 3, 4, 5. So it's 5 carbons. And then they're adding some variety of number of carbons and all the other problems. Sometimes they even boldface the attacking carbon with a little dot. Okay, so what about the top one, D2O? That one's actually an exception because it's not actually forming a carbon-carbon bond. It's just attaching, that nucleophilic, highly basic carbon is attacking deuterium. So the answer is really just going to be also 5 carbons, and you're just going to get the that. So it's 5 carbons now. You have a deuterium, right? Okay, so then we got this one, and this is 5 carbons plus 1 carbon. So the answer, and this is also a typical CC bond forming reaction. 5 plus 1 is 6, and so the product should have 6 carbons. You can check that. And of course, which carbon is this attacking? It's attacking this one. And also, if you're attacking a formaldehyde, you should make a primary alcohol, right? Okay, I don't want to show the mechanism for all of these, but maybe a couple just to remind us. And how do we draw the mechanism? Maybe you can, whoops. Maybe circle the bond, and go attack the formaldehyde. And I don't have room for the entire mechanism, but this just shows the basic idea, right? Carbon attacks carbon, and you get a primary alcohol. Primary alcohol, right? Carbon attacked carbon, and now you have a primary alcohol. How many carbons should this have? If we had 5 here and 1 there, it should be 6. Let's double check that we have 6 carbons. Well, we got 1, 2, 3, 4, 5, and 6. Where's the squiggly line that showed the CC bond that we formed? Well, it's right there, and that shows, you can see, look at the squiggly line and relative to the OH, and see that, and that's what you always get when you attack either formaldehyde, aldehyde, or a ketone, is the squiggly line is directly next door to the oxygen. Okay, so what about this one? Now it's an aldehyde. What kind of alcohol do we get if a Grignard attacks an aldehyde? That will be a secondary alcohol. I guess, I can draw little arrows, I guess, for each of these. We'll see if it gets too crazy. But yeah, it attacks there. Which carbon is it attacking? Obviously this carbon, right? How many carbons are being added? 1, 2, 3, 4. So 5 plus 4 is 9, so we can double check our counting. Make sure we get 9 carbons in the product, and also, I'm not showing a full mechanism, but like a little mini mechanism that attacks, and then the water will protonate the O-. So essentially it's going to be this structure, and then 1, 2, 3, 4 carbons more. So we could try to draw that like there, and then this is that 5th carbon, and then it is attached to another carbon, and then there's how many more? This is the second dot. And how many carbons do we have? 1, 2, 3, 4 more. 1, 2, 3. There we go. And what is missing in the final product? All of these reactions make alcohols. So there's our secondary alcohol. Okay. Now this is an epoxide, and this is kind of one of the new Chapter 9 problems. If we're just considering carbon counting, well, we have 5 here. How many carbons here? 2. 5 plus 2. It should have 7. But the difference here is that when this I'm going to stop drawing the arrows because it's going to get kind of, well, maybe I'll sneak an arrow in for this one. So I'm going to go for my little circle. Start from the circle, go from the circle, and I'm going to attack, you know, in this side doesn't matter which side of the epoxide we're attacking. It doesn't matter because it's 2 carbons, and they're equally, you know, not sterically hindered. So if we come in and attack, I'll attack the left side, for example, breaks it open, it's a spring-loaded electrophile. Now, how many carbons are we going to have? 5 plus 2 is 7. So I'm going to redraw the nucleophilic part, and this is the 5th carbon. And then how many new carbons? When we attack that epoxide, we'll have 2 new carbons. There's the dot, and then the other one's the non-dotted one. Just add a little dot here. Cool. And where is the oxygen now? I mean, if the Grignard attacked the left carbon, forced the oxygen onto the right carbon, then this was the nucleophilic carbon, this is the electrophilic carbon. Where's the oxygen? Well, it's there. Cool. That is a, what kind of alcohol is that? It's a primary alcohol. Where's the squiggly line? It's right there. And that's kind of the dead giveaway of what happens when you attack an epoxide, is that the OH is on the neighboring carbon from where the squiggly line is, right? The squiggly line's there, oxygen's on the neighboring carbon, it's an epoxide. Okay. And how does that differ from the first primary alcohol we did up top with formaldehyde? Well, in that case, we directly attacked the carbon, kicked electrons up, and then the squiggly is directly adjacent to the OH. Alright? What happens now if the squiggly, or sorry, the Grignard attacks a ketone? And where do we attack? Which carbon do we attack? Well, we attack the ketone C double bond O, this is right there. Yeah, I wasn't going to draw the little arrows, but I think I might be able to squeeze in all the arrows. Of course, the nucleophilic bond, or it's a carbanion, remember it's basically a C minus, is going to attack the ketone, so we can draw a little arrow in right there. Attacks the ketone, and then where do the electrons go? Up onto the oxygen. What kind of alcohol do you get if a Grignard attacks a ketone? Primary, secondary, or tertiary? It should be tertiary. So let's put it all together. How many carbons will we have in the product? We have 4, 5 here, and then we have 1, 2, 3, 4. So 5 plus 4 is 9. So let's put it all together, and you know, you can, I mean, this is, I usually start with the Grignard, and then I add the other part. So we'll start with the Grignard, and here's our first dot. And where's the second dot? Well, we'll put it right there. What is on that second dot? You have a methyl, you have an ethyl, you have an O minus. So we have a methyl, we have an ethyl. I'll just arbitrarily draw the O minus, but of course after the H2O it becomes OH. And what kind of alcohol is that? It's a tertiary alcohol. And where's our squiggly line? Right there and right next door to the oxygen. Cool. Let's just add the types of alcohols to the other ones. Which one? This happened to be a primary, but it was a different primary than the one we did up top with the formaldehyde, right? This one, when we attacked an aldehyde, what kind of alcohol do you get? A secondary alcohol. And this was kind of the normal case of making a primary alcohol from formaldehyde. Alright. Alright, what do we got next? Still got the same Grignard, and this is an interesting one. This is a epoxide of how many carbons? 1, 2, 3, 4 carbon epoxide. So 5 carbon nucleophilic Grignard, 4 carbon electrophilic epoxide. When we're attacking this epoxide, and you know, remember that these Grignards are basic. They're not non-acidic. Because when you got acidic nucleophiles like HBr, the behavior can be a little funny for epoxides. But basic is always going to be Sn2, meaning, is it going to attack the left or the right? Sn2 is dependent on steric hindrance, so it's going to attack the left here. It's going to attack the left to avoid the steric hindrance of this ethyl group. So maybe I can squeeze in another arrow. We're going to attack the left. If you like, we can do the little bold-faced dot thing. So dot and then bold-faced dot here. Alright, dot dot. And then we're adding 4 plus 5 is 9, so we can check our math, our accounting, and make sure we don't screw up the carbon counting. Alright, so I recommend just redraw this guy and the 5 carbons of this, and we'll just do that. There's our 5 carbons, there's the dot, and then we're adding how many carbons? 1, 2, 3, 4. So we could, you know, start with that one. And what is on the dot? Well, nothing except the, right? Because the oxygen is not on where the dot is. The oxygen's on the next to our carbon. So we can draw, basically add our 4 carbons now. 1, 2, there's our 4 carbons. Alright, 4 carbons. And where's the, relative to the second dot, where's the oxygen? Is it on that carbon, second carbon, third or fourth? It's on the second carbon. And then you have an ethyl hanging down over there. So yeah, we got OH. Where's the squiggly line, and where is the squiggly line relative to the OH? Okay, well, it's right there. And traditional for epoxides is when the squiggly line is 1 carbon away from the OH, that's what you expect from an epoxide. Cool. So, and what kind of alcohol is this? This happens to be a secondary alcohol. Great. Alright, what do we got in this last example? Now it's just another epoxide. So we're going to attack the left side or the right side of the epoxide, and the Grignards will always attack the least hindered side of an epoxide, so it'll attack, in this case, the left side. So I'm going to start from my little circle that we drew, the little circle where the bond is, carbon to magnesium bond. Sneak it up and attack. There. Again, in a exam setting, you don't need to draw. Whoa! Oh, there we are. Yeah, you don't need to draw these arrows, but I think it is helpful, and maybe the dots too. I think the dots help too when you're drawing the product. So dot dot. We're cool. What's the final product look like? Start with our 5 carbon piece with a dot, and then we're connected to another dot. And what is on that dot? This is a 5-member ring, a 5-member ring. So we draw our 5-member ring. 5-member ring. And on the neighboring carbon, which I'll just assume is up top here, you have the OH. And what else do you got? You also have a methyl. There's a CH3 group right there. So there we go. And let's do our mathematical counting check. So we started with 5. We add how many here? It looks like 5 and 6. 5 and 6. So 5 plus 6 should be 11. Let's see if we got 11 carbons. We have 5, 6, 7, 8, 9, 10, and 11 carbons. It looks looking good. Where's our squiggly line? It'll always actually be between the dots, which is cool about the dots. When you use the dots, you can kind of, you know, quickly figure out where the attachment point is, or the squiggly line. That's that page. Okay, so given all that, now we can do this. This sheet's pretty cool, where we kind of work backwards a little bit, and we can see, you know, if this is a nucleophilic Grignard, well, this has to be an electrophile. Step 2 for all of these reactions, not every reaction, but all these Grignard style reactions is always water, so that's easy. How many carbons are we adding? 1, 2, 3. We have 3. We're adding 1. Where's the squiggly line? You could draw the little squiggly line, and now it looks like a must be how many carbons at step 1? It's 1 carbon. I often will also cover up the part that's not changing, the propyl grignard. Well, the propyl is we can cover it up and then see, oh, it's a 1 carbon piece. There's only 1 carbon piece you can use, and that's formaldehyde. Remember, this is not formaldehyde. This is the product of the reaction, which is a, what kind of alcohol? A primary alcohol. And when the squiggly line is right up next to the OH and it's a primary alcohol, it's always formaldehyde. Reserve formaldehyde, alright? Cool. I don't know, do you want to go down or sideways? Let's go sideways. Let's do it by counting first. What's step 2? Water for Grignards. We got 2 plus, well, it's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So 5 minus 2 is 3. Also, where's the squiggly? I mean, if you have 2 carbons here, you can kind of see, well, those are the 2 carbons. Squiggly is right up next door, and we can cover this up. Tertiary alcohol is made from, well, your 4 options would be formaldehyde, aldehyde, ketone, or epoxide, but with a squiggly right up next to the OH, it's not an epoxide, it has to be a ketone. And the structure of the ketone is how many carbons? 1, 2, 3. 3 carbons, acetone. See, we're getting in the groove here. This one's a little weird, maybe, because before we were given the Grignard and we figure out the, given the nucleophile, figure out the electrophile product. Here it's like, given the electrophile, figure out the nucleophile, like a Grignard piece, and then step 2 is always water. So it looks like, I mean, I see the 2 carbons in the oxygen. That's probably going to be these 2 carbons, and the oxygen is from the epoxide. So where's the squiggly line? It's probably going to be 2 plus 2 is 4, right? So cool. So where's the squiggly? It's between the 2 and the 2. Okay, so we could even, if we want to do our little dot mechanism, we can do dot and dot. But how many carbons are in the Grignard, and what does the Grignard look like? It's a 2 carbon Grignard. It's that with an MGBr. Remember, you can do MGBr or you can do Li, lithium. So we could either do MGBr, 2 carbons, or we could do lithium. That's equally acceptable, ethyl lithium. And if I want to do the mechanism for it, which is not necessary in this kind of problem, it would look like, well, like that. Of course, once you rearrange it, it looks like the final product. Great. Here's another one, just rearranged a little bit. Well, it's a secondary alcohol. We give you the formaldehyde, so it's, or the aldehyde. Give you the aldehyde, so you don't have to figure out what the electrophile is. All you got to figure out is the Grignard is. So we can see this 3 carbon piece, 1, 2, 3. Where do we see that here? 1, 2, 3. Okay, so where's the squiggly? It's right before the first carbon. What is the structure of the Grignard type or organolithium? Well, you just get your finger out or your hand and you cover up with the right side or the left side should we cover up? Well, obviously these carbons are from the electrophile. We care about the nucleophile, so we just cover up there. And don't lose that. There's a carbon there. It's going to be a ch2. So it's going to be a benzene, ch2, and then MGBr. So it's benzene, and then what am I missing? That extra carbon. I could go up and over, or I can go from the bottom. It doesn't really matter. And then it just matches what I see there. If I want to do a mini mechanism, I could circle the bond and go attack the aldehyde. Okay. All right. What about this one? Now I'm giving a Grignard. A nice Grignard with a cyclopropyl and a methyl or ch2. You can definitely see the correspondence between these. You should be able to see the squiggly line. Where's the squiggly line? It is right there. That's a squiggly line. And is a squiggly line its position? Does it indicate that we're attacking in the box what? Is it formaldehyde? Is it a aldehyde? Is it a ketone? Or is it an epoxide? Well, it's a tertiary alcohol. Tertiary alcohol. And it's a tertiary alcohol, and the squiggly is right next to the carbon with the oxygen, so it's either a ketone or an epoxide, and it's going to be a ketone. So because the squiggly is right where the next door to, I mean adjacent to where the OH is. So what do I draw here? Cover up this part, and now you can see that as a ketone would be a 6-member ring with a ketone. If we want a mini mechanism, don't draw that bond attack, it's this bond. It's the carbon-magnesium bond. And that would make that tertiary alcohol. Now, this last problem is cool because it's very similar. The last problem is cool, it's very similar. It's the same thing except the OH is on the neighboring carbon. Oh no, what do we do? Well, first start with the squiggly. That's not the obvious squiggly. And now the question is, if the squiggly is not directly adjacent to the OH, but on the adjacent carbon, then that would suggest formaldehyde, aldehyde, ketone, or epoxide. The answer is epoxide. So all you got to do now is also cover this up and envision an epoxide. What does an epoxide look like? It's a 3-member ring with an oxygen. So start with a 6-member ring, and then that oxygen will really be bound to both carbons. But the best way to draw it is just 6-member ring, and then an epoxide like that. Okay, so next thing on this review sheet is the some examples of ether cleavage, and I give a hint that you should step through the mechanism and draw the protonated ether. That's going to be the case for ethers and also epoxides if we're kind of confused on the mechanism or how they open. So I start with the easy ones and I go to the more complicated ones. This is an easy one. Hi cleavage of dipropyl ether. And the other thing, on the actual sheet, these are color coded, but this is like Sn2. This is another Sn2, and then we have an Sn1, and we'll explain why that one is Sn1. And then we have E1 cleavage, and we have enough space to do the mechanisms, so we'll draw kind of like little mini mechanisms for these ones also. Okay, so dipropyl ether, Sn2 cleavage, and it's a nucleophilic acid. HBr, HI, HCl, those are nucleophilic acids. So to do the mechanism, I recommend protonate the ether. So start with the oxygen attacking the H, kick off I, draw the ether again, and a proton, and a plus charge. Okay, so then I'll draw I minus up top here. Now I minus in an Sn2 reaction is deciding should I attack the left or the right, and well, there's no difference, left, right, whatever. And so the cleavage reaction will basically create an alcohol and a alkyl halide, and I think alkyl iodide. I think I say that in the box. Alcohol, alkyl iodide. Alright, so I'm going to attack the left. Well, actually, if I'm following the boxes, maybe I'll attack the right, because the right side said alkyl iodide, and we'll just keep consistent with the boxes. So iodide attacks. What does that create? It creates a 3-carbon alcohol and a 3-carbon alkyl iodide. That was easy, right? 3 carbon alcohol. I'm just being consistent in the structures, that's not really that important. 3 carbon alcohol and 3 carbon alkyl iodide. Great. Okay, so another Sn2 cleavage of an ether. So let's protonate the ether. Circle, draw a lone pair, circle lone pair, attack, break it open. Anything missing? The charge. I'll draw Br minus, and Br minus could theoretically attack the left side of the protonated ether, or it could attack the right side, but it is going to pick which side in an Sn2. It's going to pick the least sterically hindered side, so it's going to attack the left side. And if it attacks the left side, what happens to the protonated oxygen? It breaks off, and now the products are... I tricked you here. I put them in opposite order. So, but the alcohol will be how many carbon alcohol? It'll be a 3 carbon alcohol, isopropyl alcohol. And on the other side, it's a 2 carbon alkyl halide, bromoethane. Okay, so SN1. Why was the top one's SN2 cleavage? And this next one will be SN1 cleavage. What's the reasoning for that? Well, the top ones were either a primary on both sides, or in this case it's like a primary slash secondary ether, primary on the left, secondary on the right. But if any of the sides are tertiary, then it goes, and it's HBr, or nucleophilic acid, then it's going to go SN1. It's going to go SN1 cleavage. And now the Br will not go to the least substituted side, it'll go to the more substituted side. So how does the SN1 cleavage work? Start with the oxygen, grab the proton, do the same exact thing. Protonate the oxygen. Alright, so we protonated the oxygen. So what happens in an SN1 reaction? Does the nucleophilic Br just go attack? No, it doesn't. What actually happens now is we have a tertiary carbon with a good leaving group. That is a leaving group, and the leaving group leaves. So the leaving group falls off, and that makes the alcohol. How many carbons are on the alcohol? 3 carbons. And then what happens to the other piece? What forms? How many carbon piece? 4 carbon piece, and it's a carbocation, a tertiary carbocation. And then Br minus attacks that. And what forms? What happens when Br minus attacks that tertiary carbocation? It forms a bond to it, and then it makes an alkyl bromide. So now the Br went to the more substituted side when it does an SN1 cleavage, and that contrasts from the last one where the Br went to the least substituted side. All right, that's an SN1 cleavage. Now what happens if you do, we're only showing the example of a tertiary with a non-nucleophilic acid. So non-nucleophilic acid like H2SO4, tertiary, and that's going to do an E1 cleavage to make an alcohol and an alkene. So how does that work? Same way, so we're going to start with the oxygen, draw the protonated ether. Nice protonated ether. And what's going to happen? It's the same exact thing. with this non-nucleophilic acid. So we're just going to cleave the protonated ether, and that makes an alcohol. How many carbons in the alcohol? Looks like it's 1, 2, 3, 4, 5. A 5-carbon alcohol with a branching at the end. So that looks like there we go. Primary alcohol. And then what's the other thing that forms a tertiary carbocation? Right? And what's the fate of the tertiary carbocation with a non-nucleophilic acid? So not like HBr. What happens? I usually draw like water, and the water will take the proton and make a what? Water takes the proton and makes a alkene. So a nice 4-carbon alkene. So that's the product of the cleavage of a tertiary sided ether with a non-nucleophilic acid via E1 mechanism. This is also a protecting group, right? We talk about how terbutyl ethers are a protecting group. I'm not going to review that extensively now, but that'll be on the exam. You should review that. And this is the cleavage of a tertiary ether, or a terbutyl ether, okay? Okay, so next we're going to move to epoxides. It's nice to compare epoxides and ethers, and the kind of, you know, cleavage of an ether versus the opening of an epoxide. Now, if it's a non-acidic nucleophile, which could be, you know, typically it's basic, but it's not always basic. It's just the point is it's not acidic, so it's not like HBr. It's always Sn2-like. And that means the nucleophile will always go to the least hindered or more hindered side. Always the least hindered side. Okay, so let's jump in and this, you know, KCN, we've seen that as early as chapter 6, I think, with Sn2. Well, it's just an Sn2 nucleophile, so it's C triple bond N dot dot negative is the key part. Remember also with these, we talked about crown ethers, and crown ethers would solubilize like the K plus portion of that, and sometimes we'd add like 18 crown 6, C6. That was in chapter 9. You can review that if you like, but sometimes we do that, and basically 18 crown 6 surrounds the potassium, and then the Cn minus goes and does its attack. So Cn minus can attack the top or the bottom here. In Sn2 style, non-acidic nucleophile. It's not basic, but it's not acidic either. So it's going to attack the top or the bottom. It's Sn2. It's going to attack the bottom. So how's that work? I can do the mini mechanism. Attack. I'm skipping the O minus intermediate, but temporarily you'll have an O minus, and then the Cn is attached to the bottom carbon here. So alcohol, nitrile. Cool. Next one, another Sn2 style one with a you know, common Sn2 nucleophile, thiolate, sulfur isopropyl thiolate. For sodium, if you were thinking about crown ethers, it's not 18 crown 6, it's 15 crown 5. You don't have to memorize which is which, but you might see these on the exam, so just be right, you know, don't be alarmed. So Sn2 style opens on the left or right? Well, the left is the more hindered, the right is the less hindered, so we're going to attack the right side here. Open up the epoxide, and where is everything? We're adding a 1, 2, 3, 4, 5 carbon piece. 1, 2, 3, 4, 5. Of those carbons, where's the oxygen? It's on the 1, 2, 3, 4th carbon. So 1, 2, 3, 4. And what's connected to the 5th carbon now? the sulfur. So let's make sure we draw a nice bond to sulfur. Now we still see our 1, 2, 3, 4, 5 carbons, sulfur, and then the 3 carbons of the isopropyl group. My bond is a little funny, let's fix it. There we go. What functional group is that? It's a sulfide. Cool. Alright, now this is also the case for Grignards. So this Grignard is attacking, this benzene or phenyl Grignard is attacking a 3-carbon epoxide. Are we going to attack from the left or the right? We're going to attack, in this case, from the left, the sterically more available side. Mini mechanism. So product has, we have 6 carbons on the left, 3 on the right, so 6 plus 3 is 9. We can double check our work. Benzene, how many new carbons? 3. Of those 3, where is the oxygen? Is it on the first, second, or third carbon? Well, we open it, we attack the left, pushes it onto the middle, so the end of product has an OH. And initially you have an O minus on that carbon. Alright, what about this one? And this is interesting because it is a tertiary epoxide. There's a tertiary side. And when you have acidic nucleophiles like HBr, then the nucleophilic Br will actually attack the more hindered side. But this is not acidic. This is still basic, or let's say non-acidic. So, but the fact that it's tertiary does not matter for these kind of Sn2 openings. So we're adding 3 carbons, and with this lithium I'm just going to draw the bond. That's going to do the attack. We're going to attack the top or the bottom. We're going to attack the bottom. There is the 6-member ring. Our propyl got attached on the bottom. Here we got the methyl and the OH. Where's the squiggly? It doesn't hurt to draw the squigglies. I think it's actually helpful to us. There's a squiggly. Alright? So those were opening. Where's a squiggly in this last one also? It's right here, very obviously, and this 1 carbon away from the oxygen. Okay, good. So these were the openings of epoxides with non-acidic nucleophiles that are all Sn2-like. Alright. What about opening epoxides with acidic nucleophiles? And these will either be Sn2 or Sn1, depending on the epoxide. If it is I'm calling this like a primary / secondary epoxide, because you have like a primary side on the left and a secondary, primary on the right, secondary on the left. It's going to be Sn2-like, and it's going to be kind of like our last examples with the Grignards and non-acidic nucleophiles. But for all of these ones, I think I should make a note to draw the protonated epoxide. That's really helpful. So start with the epoxide. Get that proton on there. A nice protonated epoxide. Okay, so now in an Sn2 like cleavage, Br minus is going to attack the left side or the right side of the epoxide. It's going to attack the least hindered side, which would be left or right. Attack the right side. Sn2 attacks the least hindered side, opens it up, and now you get, those are the carbons, right? 1, 2, 3, 4, 5. Where of those, if I call them 1 through 4, where's the oxygen? It's on number 4. The Br is on the 5, assuming that numbering system. Cool. That was Sn2-like. Now if you have a tertiary side to the epoxide and an acidic nucleophile, it's going to be Sn1-like. So how's that look? protonate. Protonate the epoxide. Alright, and what happens in an Sn1-like reaction, ethers or epoxides? You cleave the, or in this case you open it. So you're going to open it to make what kind of carbocation? A tertiary carbocation there, or a secondary carbocation there? The answer is to make a tertiary, because tertiary are the favorable ones. So to draw the mechanism, let's see if I can zoom in a bit. It's going to be basically an arrow that looks like that. So from the bond to the oxygen, from the bond to the oxygen, what does that make? Well, we got that. We have the methyl. Methyl's still there. What's on the molecule? Oh, it's actually, I guess, yeah, not quite in the box yet. We have one more step here, since we're doing the mechanism. So what do we got? We broke the bond, so now there's a what there? There's a plus charge. And what's on the bottom carbon? A carbon to oxygen and a proton. It's an alcohol. Okay, so now Br minus attacks. Where does it attack? The carbocation. Now you got the bromide is on the more substitute side. So remember, how does that differ from the last one? Here the bromide went to the less substituted side. That's what you get with an Sn2-like epoxide opening. And then when Br attacks here, it attacks the more substituted side. I could draw, if I want a mechanism, I might draw it attack the top. Of course, that doesn't really matter. The point is that the bromine is on the more substituted. So the mechanism suggests it's on the top here, but I can draw it there just as well. Alright. Back to Sn2-like. Circle lone pair attack. Alright. Protonate the epoxide. And now, and now Br minus, we have a protonated epoxide. Sn2-like, because there's no tertiary center to this epoxide, is going to attack the right carbon, which is more hindered, or the left carbon that's more hindered, or the right carbon that's less hindered. It's going to attack the less hindered one on the right. What does that look like in the product? Got the benzene. Got the Br attached. Remember also that, yeah, the benzene is not really involved at all, so don't do anything with the benzene except draw it. Okay. Okay, now we have a tertiary side again, and what does that mean in terms of the opening? With a tertiary side of the epoxide and a nucleophilic acid, you are going to do Sn1 cleavage. So, protonate the epoxide. Draw it nice and big. Now you got your protonated epoxide. And what's going to happen now? Is the Cl involved yet? No, the Cl is involved later. For now, the epoxide is going to open up to make a tertiary carbocation. So there's the base chain, and here's the methyl. And where's the plus charge? Right here. Where's the OH? Right there. Cl minus. Circle attack. What does the product look like? It's this with the Cl attached. I'll just go outside the box. There's the alcohol. Cl. See it? There's the molecule. Good. I'm going to show this kind of scary, daunting slide, Chapter 12, Alkene Reactions in the Forward Direction. Now I'm recording this before you guys have even reached the end of all these reactions, but I'm just going to go ahead with them anyway, and this will be maybe more helpful when we're all done, but at this point you should know at least some of these. So, like H2 palladium. What does H2 palladium do to a alkene? It reduces the alkene to a alkane. How do we draw that? It's this minus double bond. I'm going to draw these kind of small because we're at below one space. Okay. What about HBr? What does that do? HBr is a Markovnikov addition of HBr, so that means the Br goes to the more substituted or less substituted. It goes to the more substituted. So it's essentially 6-member ring, and then you get a Br. On the more substituted, it's via carbocation, and I'm not going to draw the mechanism, but double bond attacks H from that side, and then you get a carbocation on the more hindered side, Br minus attacks. This is one at the end of the chapter, but I just mentioned it, I foreshadowed it. HBr peroxides is non-Markovnikov or anti-Markovnikov, and that puts the Br on the other carbon. So you might know the basic idea, and then you'll get the details later. Alright, I'll write Markovnikov, anti-Markovnikov for now. What about the mercury one? It's oxymercuration and demercuration. All that does is it makes a Markovnikov alcohol. So an alcohol at the Markovnikov position. Now the mechanism was kind of a little more work, but I provide a sort of a mini mechanism, a simplified mechanism. BH3, I call this OMDM, oxymercuration, demercuration. That's sort of my abbreviation for the name, which is oxymercuration, demercuration, OMDM. This BH3 one gives you the anti-Markovnikov alcohol. So this is Markovnikov, this is the anti-Markovnikov alcohol. And this is called hydroboration oxidation. I call this HBOX. This is my own personal abbreviation. OS4, osmium tetroxide. This thing makes essentially a double alcohol, so you get 2 OHs. And it's OSO4 and then like H2S or Na2S. Sulfur, some kind of sulfur thing. It was typically H2S, water. Alright, what's this? This one, O3 is ozone. And ozone cleaves alkenes, so it basically snips the alkene into 2 pieces, so that it breaks the alkene into 2 parts. Basically it's going to make a ketone on one side and aldehyde on the other. And I usually draw them poking at each other. So looking at that molecule, let's the way I draw ozonolysis, which is an alkene cleavage reaction. It will look like a ketone. And I'm going to draw kind of an extended looking molecule, aldehyde. And I have them poking at each other. See that? Ketone, aldehyde. So basically the C double bond C you've got cleaved into 2 parts. Okay, Br2. Br2 just dibrominates the alkene. Br2 water is the same as Br2, except alcohol from the water will be at the more substituted side. So we talked about how that happened mechanistically. It's essentially the same thing here. but you got an OH on the more substituted side and a BR on the less substituted side. Alright? MCPBA, you actually learned this maybe a chapter or two ago. MCPBA makes a what? An epoxide. So MCPBA creates epoxides and alkenes. And just review of epoxide chemistry. What does a Grignard do? It's a non-acidic nucleophile. It attacks the more substituted or the less substituted? It will attack the less substituted. What's pH? pH is benzene. I'm just an abbreviation for benzene. I'm just going to use the abbreviation. But essentially it just attacks right there, breaks it open, and then we'll get alcohol, benzene, pH for the benzene. Okay, I can't do the mechanism for HBr here, but essentially, noticing that this has a tertiary side to it, HBr, acidic nucleophile, will actually put the Br onto the more substituted side. So rather than benzene attacking from the right side here, the Br will attach to the left side. You can practice the mechanism if you like. And you get alcohol here. So try that mechanism if you want more practice. Okay, that's what HBr does to that epoxide. So we just did all of these ones. Oh yeah, there's this one. May or may not get to this one. Sometimes this will be an extra credit one. Chloroform, CHCl3, and a strong base like potassium terbutoxide. This makes another cool thing, and it makes a cyclopropane ring. So, you got your 6-member ring and you got your methyl. Essentially what it does, and there's an interesting mechanism to this, and sometimes this becomes extra credit on the exam, but it actually builds a 3-member ring. A 3-member ring, cyclopropane. And in this case with CHCl3, 2 chlorines get added, and I'm just going to draw a little Cl there and a Cl there. So it's, two chlorines are on the cyclopropane. So depending on the time, we cover this or we don't cover it, and sometimes it's extra credit type thing. Okay, so that's that. Alright, so now this is the same kind of problem, but we're given the products and we have to review what the reagents are. And it's often kind of obvious, like if with an alkene to the dibromide, any guesses what the reagent is? Well, it's Br2. That's easy. What if we're adding a single, when we're doing this one, we're actually adding an H and a Br, but we're not showing the H here. Of course, and it's Markovnikov, right? So Markovnikov hydrobromination was HBr. Easy. What about reduction of the alkene to an alkane? It's H2 and maybe palladium or platinum. H2, palladium or platinum. Markovnikov alcohol formation. Oh no, that's one of the weird ones with the weird metals and stuff. It's the mercury one. It's a 2-step process. And you know, knowing a couple elements of this will probably get you through the exam. You know, flash memorizing the specific reagents might be hard, but at least knowing what metal it is for Markovnikov. Was it osmium, or was it mercury, or was it zinc? I don't know. What do you think? This is the OMDM, oxymercuration demercuration, and the reagents were HgOAc2, mercury diacetate, water in step 1, and then step 2 was NaBH4. So the water is part of the mixture there. So this combination of reagents makes the Markovnikov alcohol. Okay, through the mercuronium intermediate, which is like a bromonium. Okay, and if we wanted 2 alcohols, this is the one that uses osmium, and so it's OSO4, osmium tetroxide, OSO4, and usually like H2S and a water, some sort of sulfur source. Okay, this looks like we're adding a H on one side, a BR on the other side, but it's not Markovnikov, because that was Markovnikov, HBr. This is Anti-Markovnikov, what was it? It was HBr and something else. Peroxides. HBr peroxides is the anti-Markovnikov formation of a bromide. Okay. This is the one with chloroform, so HCCl3. Often you'd see these and you'd recognize the reagent, and then you're adding the product. ch8, but also index cards are a way to help recognize these reagents even more. HCCl3, or sometimes we say CHCl3, same thing, chloroform. This is often an extra credit one. Okay, now we're adding an oxygen and a BR, so it's BR2, water. That was also BR2 and water, okay? That was essentially BR2 alone mixed two bromides, but when you have water it adds a oxygen to the more substituted. Epoxide. What was epoxide? MCPBA. How do we add apparently an isobutyl group to that epoxide from the least hindered side? Well, we just add that thing as a Grignard, so it's BR and water. Okay. Alright, and what about cleaving the ether, the epoxide, and putting the BR on the more substituted side? How did that work? This is one of the ether cleavage epoxide opening reactions, and we're adding HBr, so there's H and BR, and when you do that, the BR goes to the more substituted side, so it's HBr. You can practice that mechanism. See if you can get from there plus that to that. All right. This one, I guess we may or may not have covered this one in class. I think we might have skipped it. But this one is actually just lithium. I think we did mention it. Lithium aluminum hydride is a hydride nucleophile. It's essentially H dot minus, and it opens up epoxides like that. So that's maybe a little less common and less important, but it's just another way you can open up epoxides. Okay, and then what about cleavage of an alkene to a ketone and an aldehyde? And I just opened up the molecule so you could see it all. That was the ozone, O3, zinc and acetic acid, HOAC. Ozone and zinc acetic acid. Okay, what about another? So we did one alcohol before. This is Markovnikov. Used mercury and oxymercuration, demercuration. What about alcohol on the anti-Markovnikov side? And that is the other one. This is the BH3, H2O2, NaOH. So that's the anti-Markovnikov alcohol formation that's kind of complementary to the Markovnikov alcohol formation. So these two are kind of hand in hand. And then the other weird one that's related to both of those is the one that makes two alcohols. It's called, that's osmium tetroxide. We call it dihydroxylation because we're adding two hydroxyl groups. Okay, great. Hopefully that helps in your study process. Obviously just write these down and you can use this in your sort of flash memorization of these reactions.